pointer is a variable that stores the address of some other variable. But what is an address, and where are variables stored if other variables can store their addresses? Well, a computer's memory typically consists of 8-bit bytes in one continuous sequence. Portions of this memory are reserved when a program starts to store program code, static or external variables, as well as to contain the stack of function calls, their arguments, local variables, and so on. The storage for each variable must reside in memory, and where it resides is defined by an address. Every variable has an address, even if you don't use it or think about it. This address is just the offset from the base address to the location where the variable storage resides. Now, C provides a special category of variables specifically for handling these address variables, and they are called pointers. Pointers or pointer variables also include a type that indicates the type of the variable being pointed to provide a degree of safety, as the compiler can check that you are using the variable being pointed to according to the rules governing that particular type. Sometimes you need to throw away the type of a pointer. There are many reasons you might need to do this, but you should always do this with some caution. Still, for those times, C provides a special type called void, which in this context means some storage whose type is not known to the compiler. The base address of 0 is also treated specially, not so much by the compiler, but by you and I in particular standard libraries to mean a null pointer, or a pointer that is not currently pointing to anything. The simplest way to start using pointers is to get the address of some variable. I can define a local variable called apples. This variable is stored on the stack, in memory, and you don't have to think about where or how it's stored or how its storage was provided, but you can get its address using the address of operator. That's the ampersand, which is a unary operator that I've not yet introduced and has nothing to do with the bitwise AND operator, which, as you know, is a binary operator. The address of operator returns the address of some object. In this case, the object that the apples variable refers to. I then use this returned address to initialize the p variable, giving it an initial value. The asterisk or star following the type and preceding the pointer variable name indicates that this variable, which is also stored on the stack, is a pointer to int, or a pointer variable storing the address of an integer object. Again, this star has nothing to do with the arithmetic operator. Now, pointer declarations can get complicated. This is really simple, but as you will see later, it doesn't always stay this simple, and I've found that it helps to read such declarations from right to left. Start with the name of the variable and move back until you reach the beginning of the declaration. When you see the star, just say pointer. So p is a pointer to int, and it's initialized with the address of the apples variable. Now we see another use of the star, and in this case, it is another unary operator that returns the contents of its operand. This is often called the dereference operator, as it dereferences the pointer, returning the variable being pointed to. So here we see an expression, and you can read it as the contents of p plus 6. The result of this expression is then used to initialize the oranges variable, giving it an initial value of 11. Now, a key insight to remember when using pointers is that the compiler is usually unable to detect whether pointers are in fact pointing to some valid location. C also does not offer any runtime facility for making these sorts of checks. Consider this scenario. We have already learned that local variables are not initialized, so the value of the p local variable, or the address that it initially points to, is not predictable. It could be anything. So when subsequently executing this line, what happens? Well, nobody knows, and this is where pointers get ugly, because your program will just go on and treat the contents of the address being pointed to as if it is an integer. Assuming the address is in an addressable range, your program may continue to run without realizing that its results are quite likely incorrect and poisoning the rest of your program and the user's information. A much better scenario is if the p variable is initialized to 0. In this case, you can be sure that your program will crash very abruptly. What that means depends on the OS, but your program won't simply continue running, causing more harm. Obviously, some defensive programming will go a long way. Given that we all agree that a null pointer is an invalid pointer, and null is represented by 0, and 0 is treated as false in C, we can simply use an if statement to check whether the pointer points to anything before using it. Pointers and arrays are very closely related in C. In fact, the language constructs for pointers and arrays are largely interchangeable. You can use the syntax that most conveniently solves the problem at hand. First, let me show you how to define an array. We can then see how it can be manipulated in various ways. An array of a certain type is defined using square brackets following the name of a variable. In this case, enough storage is provided by the stack to store 5 continuous integers. This continuity is critical for its efficient manipulation. Like other local variables, the array is not initialized to any meaningful value unless you yourself initialize it first. You can do so with an alternative syntax. In this case, the array size is not given, but the compiler easily deduces it from the initializer list. Alternatively, you can explicitly provide a size, and then you have the option of providing fewer values during initialization. In this case, the array has exactly 5 elements as declared, and the remaining elements are initialized to 0. A common shorthand then is to initialize an array of arbitrary size to 0 simply by providing an initializer list with a single 0 element. The primary restriction is that the array size has to be a constant. In C, the only thing that practically works as a compile time constant is a literal or a preprocessor definition, which amounts to the same thing. Along with defining array variables, the square brackets are also used to refer to a specific element of an array. Given an array definition such as this, we can use square brackets, known as a subscript operator in this context, to refer to a specific element of the array. In this case, we're using it as the target of an assignment statement to set the value of the first element. C naturally starts counting from 0, as this makes various pointer-based algorithms very efficient. You can also use a subscript in an expression to return the value of a particular element. Now let's take a look at how pointers can be used to achieve the same. First up, you can easily turn an array into a pointer simply by assigning or initializing it as such. You can also get a pointer to a specific element by subscripting it and then using the address of operator to get the address of the element itself rather than the value. It should be obvious now that the address of the array variable is the same as the address of the first element. What makes pointers handy when dealing with arrays is that you can use pointer arithmetic to change the element being pointed to very efficiently. You can simply increment your pointer and it will point to the next element in the array. You can even move it arbitrarily by using a relative offset. In this case, the pointer is now pointing 3 elements ahead. The thing to keep in mind, and keep telling yourself this, is that the greatest power and biggest danger with C is that it sits so very close to the machine. All of these operations map directly to machine instructions, which makes them amazingly fast, but that also means that you can incorrectly increment a pointer in this way beyond the end of the array, and neither C nor the OS will be able to tell you that you've made a mistake.